So last time we have learned the Boolean algebra with 5 axioms and 12 theorems that can be used to simplify Boolean equation. And this time we'll learn, okay, how to apply them, how to use them. Okay, what are the principles in order to use them in order to simplify the Boolean equation? And the basic principles that work for sum up products, or we can have the dual form of the theorems that will work with the product of sum. But we'll just go with one of them and it's going to be similar for the other form as the dual form. So we'll go with this one. So if we're simplifying sum of products, and because it's sum of products, it's going to go with mean terms. So a lot of the Boolean equation gonna have this similar form. You want to have the products, okay, or the inputs, or with, or that one is the sum. You know, this is the sum, and this one is the products, which is the sum of the products. Now, why? Because when we do the mean terms, they are the products of the input, okay, and then we sum them where the output equal to 1. So a lot of time when you create the Boolean equation using sum of products, your Boolean equation will have this kind of form on the left hand side like this. Okay, and also when you move the input from one row to the next row, one of them will be negative in form and the rest will be the same. One of them will be negative in form and the rest will be the same. So let's say you will see a lot like A and not A like this. Okay, and if we see something like this, it's going to be P only, or A and not A can simply be cancelled out. Okay, why? Because if you factor out the P, then you'll have A or not A, and A or not A is gonna be 1. So P and 1 is 1. So we apply the complement and the identity theorems. We'll have this. Okay. Then we'll define some other term which is called the prime implicant. So the products like this is called an implicant, and it is prime if it's minimal or it cannot be reduced any elements anymore. Okay, so let's say this P and A is an implicant, but it's not prime because A can be eliminated, which is not A. Okay, so but P is a prime one because it's you cannot reduce it anymore. Now let's just go for the example. Let's just say we're going to simplify this Boolean equation. Yeah, not A, not B, not C, or A, not B, not C, or with A, not B, C. So step number 1, we can apply distributivity, which means we factor out not A, not B because they are the same. Now we are factoring out not B, not C, not B, not C over here because they're the same. Then which is the first two. Then the third one just simply go down there. Then inside we'll see not A or A. Okay, we'll see not A or A. Then because we'll see not A or A, we're going to apply the complements theorem and it's become 1. So we apply the complements and this one become 1. Okay, and next, because not B not C and 1 is not B not C. Why? Because this is identity theorem. So it's gonna be not B not C or A not B C. So this one is identity. So this one is one solution of minimizing from this complicated one into this one. Okay, or simplifying, not minimizing, because we may not get the minimal solution by now. Then one problem with applying math or Boolean algebra into this is we may not get the best solution. Let's just say if we use the Boolean algebra to solve the same problem like this, we may first using idempotency theorem. What does that mean is B or B is B. Okay, so if you have B, you can just add one more item a B into it. Okay, and at first we'll say, man, you just complicating the problem more, but it's actually help reducing later on, we'll see. So in this case, you'll have A not B not C. So I'm just adding one more A not B not C. Okay, why? Because I want to eliminate that C, so I see the not C. I'm just add one more over there. Okay, A not B not C. So I duplicate this element. Then next we apply distributivity by factoring out not B not C and also factoring out A not B. We're factoring out A not B, A not B. Then not A or A, not C or C. We're gonna apply the complements. Then this one become 1, this one become 1. Then you're gonna have not B not C 1, A not B 1. And next we apply the identity, because something with 1 is not something itself. So it's gonna be not B not C or A not B, because we apply the identity theorems there. So we'll see that the question is which one is better. You know, this one is better or this one is better. We'll see that this one is somehow better, even though we started making it more complicated one, because we create more pairs. Okay, because if you want to eliminate, you need to have pairs. Okay, if you want to eliminate something with the negative format itself, we need to have 2 of them at least. So normally we need to have pairs. So power of 2 elements is gonna be better. Then that's why at first we added that terms in, and finally we have some better result like this. Okay? Then so what? So it means that it might require some trials and failures, and as I said, to eliminate more, we need pairs. So if you see some of the odd numbers, it's possibly be better to add or duplicate some more elements. And actually for this, we do have a technique. And we'll see, like we're saying, if you apply Boolean algebra, you may need some failure and trial in order to get the best result. But there is a technique that we'll see from here, which is K-map, okay, or canal map, and that one guarantee that produce the best result, and they base on every pair. They combine things in every 2, like 2, 4, 6, no, 2, 4, 8, so on and so forth, and keep eliminating when you see the complements of one another. And that one is a very important techniques that works better than Boolean algebra and visual form as well. So far we need to learn this too. So the next one is we're going to have one exercise, okay, which is please minimize the following Boolean equation using the learned theorems. Okay, using the learned theorem. So this one is the product of some theorems, and the result should be not A not R. Okay, not A not R, or Y equal to A nor R. Okay, A nor R. And why is this one? Because we just have our proof that we've done earlier, which is negate the both sides. Okay. Then the next part, we should be able to do some digital design.